welcome back to this YouTube channel. So today we'll be looking at October-November 2024 paper 42 from 9702 CIE physics paper. So to begin with, why did I pick question 1? Okay, so this question is actually interesting. Now why? Because the first part is more on circular motion, whereas the second part, B, they introduced the chapter of electromagnetic induction, which is very interesting because usually circular motion, like in most cases of scenario, it is paired with gravitational forces because it relates to a satellite moving in a circular motion, right? But in this case, it pairs up with electromagnetic induction. And is it possible to do it? Definitely 100% possible to do it if you understand the concept. So without further ado, let's get to it. So let's read the question. A metal wheel consists of an axle A, 8 spokes and a rim as shown in figure 1.1. Point X is on the rim at the end of one spokes. Oh, here is point X. Okay. The rim has a radius of 0.85 meter. The wheel is rotating clockwise with an angular speed of 140 radians per second. So we know angular speed has a symbol of omega. It's not W, it's actually omega, but it looks like a W. Okay, A. For point X, determine the speed. So we know the speed has a formula of V equals to R omega. So our R is 0.85. Our omega is 140 radians per second. Then you calculate this, you will get 120 meters per second. That's your answer. Now, if you're thinking like, how did I get V equals to R omega? Why suddenly V equals to R omega? Okay, so let's refresh our memory a bit. So I'm going to draw this here. This has a bit got to do with arc length that we learned in math. So this is our theta. This is our radius. And this S denotes our arc length. So in maths, we have learned that S equals to R theta. Am I right? So what is angular speed? So angular speed, the name itself, angular, shows that the angle is involved. So angular speed means angle turned through per unit time. So angular speed means angle turned through per unit time. The angle, it goes from here to here per unit time. That is what we call angular speed. Now, where does this formula come from? So this formula V equals to R omega comes from the relationship between angular velocity and linear speed. Okay, so what do I mean by that? So we know linear speed has a formula S over T. Right, S means the distance traveled. Basically, the distance traveled from here to here over time. Angular speed involves the use of angle because it's angle turned through per unit time. That's why I use angle here. Okay. Now, so we know S equals to R theta. Can we sub this inside here? Of course we can. So what will we get? We will get V equals to R theta over T. We can separate it. V equals to R theta over T. Can you see the similarities here? Which is theta over T is omega. And this will give you V equals to R omega. That is where I get this formula. Okay? You don't have to derive this formula in an exam. Definitely you do. I think the more practices you do, you will eventually understand where this formula comes from. But do not memorize the formula. You have to understand where it comes from. Very important. Understanding is very important. Okay, moving on to Roman 2. Find the centripetal acceleration. So centripetal acceleration has two formulas. There's actually two ways to do this. First way, we can just use the normal formula, which is from the centripetal force, right? So we can get acceleration equals to V square over R. Am I right? So your V as find is 120. Remember to square. Don't forget to square. Very important. Over your radius is 0.85, and this will give you, take out your calculator, and you will get 1.7 times 10 to the power of 4 meter per second square. This is one way. The other way is you have another formula, which is A equals to R omega square. And where does this formula come from? Okay, we know A equals to V square over R, right? So, and we know that V is R omega. So you put in R omega. Don't forget to square over R. This will give you R square omega square over R. The R you can cut. You will get R omega square. So this is where you get the formula. So now we sub in R, 0.85. Your omega is 140 square, and you will get the same answer. So any way is possible. It's just your way of seeing the question. It's the same thing. So this is your answer. Okay, there you go. And make sure, as I've always said, minimum answer must be 2 significant figure. Maximum, actually I wouldn't say maximum, like the next best, it would be 3 significant figures. 2 significant figure is minimum. Make sure to, if you put 1 significant figure, but your answer is still correct, you will still get it wrong. So welcome to CIE. You'll still get it wrong. Minimum 2 significant figure. Actually, 2 significant figure is basically for accuracy. Yeah. Like, so that you have a consistent significant figure throughout. Okay, so that's about it. That's about circular motion part, which is part A. Easy, right? So you scored your 4 marks in this part. Now, we move on to B. There is a uniform magnetic field of flux density 0.18 Tesla into the plane of the page. That means it's into the plane of the page. State Lenz's law of electromagnetic induction. So this is a definition that ideally you should know before going to exam hall. So what is the definition? The definition is, Lenz's law states that the direction of any induced EMF, which is electromotive force, is to produce effects to oppose the flux change that caused it. Important keyword, make sure they have the word change. Change, induce EMF, and oppose. So you have all, because these are the one that shows what Lenz's law mean. So basically Lenz's law mean whatever induced EMF produces an effect, Lenz's law says you have to oppose that effect. So let's say ideally the force is going in clockwise. Based on Lenz's law, it is supposed to go after the induced EMF is produced, it has to produce an anti-clockwise force. For example, because you oppose it. The word oppose means going in the opposite way. Okay. Second, show that the time taken for point X to complete one revolution is 45 meters per second. So actually, there's a formula where T, we know omega. Okay, wait, let me write here. Omega equals to theta over T. Am I right? And we know one revolution, your angle is 2 pi. Or in other words, is 360 degrees. But in this case, I forgot to mention as well, the angle here is in radians. Okay? So one revolution, you go 2 pi. We know what's our omega. So we can find what is our time. So, okay, omega is 140, our angle is 2 pi, and our time taken will be equivalent to 0.045 seconds, but they want in milliseconds. So ideally, when you convert this, you should get, oops, that's not the symbol for you to use, you should get 0.45 milliseconds. Okay, right, easy, right? Time taken for 1 revolution. Remember, read the question properly. They say 1 revolution, so think about it. 1 revolution, what is the angle? It's 2 pi, and we have our omega. So substitute in, you will get your answer. Alright, moving on to Roman 3. Calculate the magnetic flux cut by spoke AX during 1 revolution of the wheel. Give a unit with your answer. Okay, let's go back to the main question and see where is AX. Okay, so this is AX. So they are asking the magnetic flux that cut through for by the spoke of AX for 1 revolution. Okay, so magnetic flux has a formula of BA. If number of turns of coils are involved, then it will be equal to NBA, where N represents the number of turns of coils. So what is B? B is the magnetic flux density, while A is the area in which the magnetic flux density is flowing. So magnetic flux and magnetic flux density is not the same thing. Okay, let me explain. So imagine this is the area covered, and we have magnetic field, because they say into the page, right? Say the magnetic field. Each of this magnetic field has a density of 0.18 Tesla. All of these fields, each of them has 0.18 Tesla. So magnetic flux is calculating the product of the flux density multiplied by the area that the flux is flowing through. In other words, the field, each of this field, each one of it has a density of 0.18 Tesla. So magnetic flux is basically calculating the total of it flowing through this particular area. That is magnetic flux. So magnetic flux is the product of magnetic flux density multiplied by the area. Okay. Now, we can start calculating it. Magnetic flux density is given 0.18 T. 0.18, and area, go back up here, this is a circle, right? So the circle has a formula of area of pi r squared. We know our r is 0.85 meter. So pi r 0.85 squared. Remember to square. Okay, you take off your calculator, you calculate it, you should be getting 0.41 Weber. Your unit is WB. 0.41. Okay? Right. If let's say this was not a circle, and if let's say this was a square, then you take length times the height. Length times the height. Yeah, you take length times the height, the normal area formula. You follow the area based on the given picture. In this case, because this wheel will be put inside a magnetic field that is inside. You know, it's going inside, right? So inside means it's X, right? So where is this magnetic field in? As in which area is it covered? It's covered in the circle area. So that's why it's pi r squared. Right. Okay. Now, 4. Determine the magnitude of the electromotive force induced across spoke AX. we know that based on Faraday's law, we know that the magnitude of induced EMF is proportional to the rate of change of flux cutting. Basically, EMF is proportional to the rate of change of flux cutting, right? So then they introduce a constant. The constant is -1 dt. Basically what they're trying to say, change in flux cutting over the change in time, right? And they want only magnitude, so you can ignore your negative sign for this case because they're asking for magnitude. Okay, so what is the change in magnetic flux? We know initially there wasn't any magnetic flux. Then now they say that there's a magnetic flux into the page. So initially it was 0 and now it has 0.41 of magnetic flux, right? Based on what we have calculated here. So the change is 0.41. What is the time? And this 0.41 is for 1 revolution. Therefore, our time must also correspond to 1 revolution, which we have calculated in Roman 2, 0.45 seconds. 0.045 seconds. So, divide by 0.045 seconds. The change in magnetic flux over the change in time. Initially, there was nothing. Now, they put it in a magnetic flux. It gives you 0.41 of magnetic flux. They put you in a magnetic field, They put you in a magnetic field, and when you calculate the magnetic flux, it gives you 0.41. Initially, there was no magnetic flux. There was no cutting. Now there is, so 0.41. Basically, in other words, like 0.41 minus 0. Because initially, there was nothing, right? But you can ignore the 0 for now, because it doesn't give you any value. This, therefore, will give you 9.1 volts. So your induced EMF is 9.1 volts. Okay, last but not least, use Lenz's law to explain whether the potential is higher at NA or NX. So this is related to current a bit, because we know current flows from current flows from a lower potential to a higher potential. Am I right? Okay. So let's look back at the picture. Given that the wheel is moving clockwise, how do I know the wheel is moving clockwise? They actually mention here. The wheel is moving clockwise. And given that the magnetic field is into the page with a flux density of 0.18 Tesla. So it's into the page, it's X. First 3 words. Use Lenz's law. We have defined Lenz's law here, saying that direction of any induced EMF is to produce effects to oppose the change that caused it. So, if now this rim is moving clockwise, okay, this rim is moving clockwise. Now Lenz's law says it has to oppose the change. So, the rim will have a force acting anti-clockwise. So you take out your Fleming's left hand, okay? You have your thumb is the force, your index finger is the field, and your middle finger is the current. Now that we know it's into the page, the magnetic field is into the page, so point your finger into the page. Your magnetic force, according to Lenz's law, now is going to oppose the clockwise force. So now it's going to move anti-clockwise. So your thumb is forward. You will realize your current finger is pointing from A to X. That means the potential is higher at X. Because like I said, current moves from a lower potential to a higher potential. Okay. So, your answer would be, first of all, we know that the force on the spoke AX must be anti-clockwise. Why? According to Lenz's law, you have to oppose it. Remember? Hence, current, I'm going to use short form here, but don't use short form in exam, okay? I means current is from A to X using Fleming's left-hand rule. So X is at a higher potential. Okay. Now, if let's say, okay, they didn't say using Lenz's law. Is there another way to solve this question? Yes, there is. Okay. You can use Fleming's right-hand rule this time. Now, why did I say you can use Fleming's right-hand rule? Because ideally, Fleming's right-hand rule is to use to find induced current. Now, why did I say induced current? First of all, I should write the word induced current here, ideally. You know why? Because there's a magnetic flux cutting. When this spoke, AX, cuts the magnetic flux, what happened? When there's a when there's a magnetic flux cutting, you're going to have induced EMF. You're going to have induced current. So more accurate, I would say, you should say induced current. Yeah. So coming back, what if they didn't say using Lenz's law? Because we can use Fleming's right-hand rule. Take out your Fleming's right-hand rule, your force, which is your thumb, again the same. Your index finger is your magnetic field, and your middle finger is basically induced current. We know we have the force, we have the magnetic field. The force was initially clockwise. Am I right? So, point down, clockwise. The relative motion, the original motion is clockwise. And it's into the pitch. You realize your middle finger is also pointing from A to X. This is another way to check. Shows that your induced current is pointing from A to X. Then, now you might be thinking, how I want to know, is it actually correct that I'm moving anti-clockwise according to Lenz's law? Get back your left hand. Fleming's left hand rule, ideally used to find the force. You have your current, A to X, and into the pitch, your magnetic field, you will realize your force proven to be moving anti-clockwise. Here's the thing, here they ask for using Lenz's law. So they start already using Lenz's law. They start the question by saying that, therefore you must say first of all, how does it oppose according to Lenz's law? The force will move anti-clockwise. And using that force, using the magnetic field, you find your current. I think the reason why they didn't say induced current in the answer scheme, it's because left hand is usually just used to find current, not induced current. But you think about it, you think about what I mean, you are cutting the flux here, Then only you can have a current flowing, right? You cannot purposely have a current flowing in your wheel, right? You are cutting the flux. When you have a cutting of flux, you're going to have induced EMF, and you're going to have induced current. And that is what Lenz's law means. Direction of any induced EMF is to produce effect to oppose it. So this anti-clockwise is opposing the clockwise, producing an induced current. Ideally, it should be induced current. So if they never say Lenz's law, you can straight away say using Fleming's right-hand rule, current is from A to X. You can just use it like that. But now, since they say using Lenz's law, you already know for a fact it's going to oppose it anti-clockwise. So it has to be the force anti-clockwise. You know where's your magnetic field, you find your current. Okay, so that's it for this question. I hope you successfully got your 13 marks. So the last part requires understanding. If you're going to blindly memorize what Lenz's law is, and you might not be able to answer this question. So understanding is very important when it comes to electromagnetism. It's really crucial because you need to visualize on how it works. So I have shown you two ways. If they say using Lenz's law, for a fact you know you're going to move anti-clockwise because it opposes the force based on the Lenz's law definition. Now if they didn't say anything about Lenz's law, they started with the fact that the potential, which direction, which end the potential is higher, you can straight away use your right hand rule. Because right hand rule ideally is used to find your induced current. You can straight away find it to find your induced current. So read the question carefully on what they want. And yeah, for IV, I want to talk about it a bit. So I feel that if you ask me personally, EMF, this formula, right, this particular formula, I think you should write the negative in the formula, but not in the answer, and final answer, because the final answer asks for magnitude. So just have to put a value in it, right? But when writing the formula, in my personal opinion, I think you should put negative. Because according to maths, if you say, let's say, F is directly, let's talk about spring, right? We know the force of the spring, and the spring there is directly proportional to the x, the extension, right? Then we say F is equals to kx, and this k is a constant. So whenever something is proportional to anything, directly, inversely, you have to add a constant to add an equal sign. So I can't simply say this is equals to this, right? This doesn't really make sense. You have to add a constant. In this case, our -1 is the constant here. So I understand if you don't want to write it in your final answer because they say it's a magnitude. But when it comes to writing the formula, I believe the correct way, you should put negative. Yeah. But final answer no need, because they ask for magnitude only, right? So you can ignore it, no problem. Yeah. But I checked the mark scheme and they did not write negative. So for the best way, I believe you can check with your respective teacher and seek their advice. But if you ask me, if it wasn't for the answer scheme, I think you should write -1. Because that's the correct mathematical way of expressing a formula, right? Yep. But other than that, everything's good. So yeah, that's about it for this question. I hope you learned something new today. I hope you learned a new way of approaching question, and I hope you understand better now. So continue practicing, continue doing a lot of question. I think by then you will be able to solve electromagnetism and circular motion question with ease. So I'll see you in the next video. Thank you for watching. Bye bye.